Now we can start talking about geometry. And geometry, of course, is the study of shapes. Now, for some people who are visually oriented, geometry comes very naturally. And other people who have not developed their visual skills, geometry can be a little bit harder. So especially for the folks for whom geometry is a little bit harder, here's what I'm going to say. It is not enough simply to watch these videos. After you watch these, get out paper and a ruler and draw these different shapes. Actually physically draw them on paper. And build shapes from physical objects. You can use pencils, toothpicks, straws, anything like that. Actually build triangles, build rectangles. Actually look at them. Use your hands. Our hands are actually part of our intelligence. So if you're using your hands, you're engaging every part of the brain, and it will make it much easier to understand all these relationships. So let's start with lines. Lines are straight and they go on forever in both directions. So here we have a bunch of different straight lines in a bunch of different directions. You have to imagine that at the end of each line there are some arrows or something like that to indicate that the lines actually do go on forever in both directions. It's very important not to confuse straight with horizontal. Those two words have very different meanings, but sometimes there are some students who confuse them. All lines are straight, so all the lines that we had on the previous slide, lines going in different directions, all of those are straight lines. And you can always assume that a line is straight on the test. If it looks straight, it is straight. That is always true on the test. But some lines are drawn horizontally for convenience, but you can never assume that lines are exactly horizontal or vertical simply because they appear so. Now, people get really confused on this. If you're confused, if you think that horizontal and straight mean the same thing, then when we say the test assumes, you can assume from the test that lines are straight, people mistakenly assume that this also means they can assume lines are horizontal, and that is not correct. A line segment is a finite piece of a line. So for example, here we have a line segment. It has two endpoints, and when these endpoints are labeled, that makes it easy to discuss. This is line segment AB. And for the purpose of the test, AB can either mean the actual shape, the line segment itself, or it can mean the length of the line segment, the numerical length. An angle occurs between two lines or two segments. So for example, here we have an angle. This happens to be between one line and one segment. The best way to understand an angle is to think of it dynamically as the act of turning or rotating. So in other words, going from here to here. That is what an angle is. It's that dynamic space in between the two lines. If we label points, we can talk about an angle. We could call this angle either CDE or EDC. Point D, the vertex of the angle right here, the point of the angle, must be in the middle of the name. And so we can call it either CDE or EDC as long as the vertex is in the middle. Sometimes in these videos I'll also use a single angle name if there's no ambiguity. For example, there's only one angle in this diagram, so I could call it angle D. Theoretically, that could occur on the test, although the test is often careful enough to use a three-letter name always for an angle. We measure the size of an angle in degrees. The test can state these directly, so 50 degrees. Alternately, the test can label the diagram and state the measure of the angle in the text, so angle GFH equals 50 degrees. Because they put letters on the points in the diagram, we can just use that to talk about the measure and the number of degrees in the text. Actually, probably its favorite thing to do is the following. Just specify an angle with a variable number of degrees. This flexible format allows them either to specify the angle, for in the text they could say x equals 50, or they could ask a question about it. They could give us other information and say find x. So they like doing this. We'll do a quick review of basic degree facts. In a straight angle, there are 180 degrees. And of course, remember, a straight line can go in any direction, but if there's any point on the straight line, all the way around from one side of the line to the other, that's 180 degrees. There are 90 degrees in a right angle. So here we have two lines intersecting at right angles. There are actually 4 right angles at that intersection. If the two lines or segments meet at right angles, they are called perpendicular. And that is a term you should know. The test can either draw that little square, the perpendicular sign, which is that little square, or it can indicate that the angle is 90 degrees. It could label 90 degrees in the diagram or have x degrees and tell us in the text that x equals 90. So there are a variety of ways that they can tell us that it's a 90-degree angle. Don't assume that two lines are perpendicular if you are not explicitly told so. This is often a trap. Suppose these points appear as part of a larger diagram and no further information is given. Certainly looks like those could be at a right angle. And that's a very tempting thing to assume. The test would love for you to make the mistake of assuming that the lines are perpendicular and that the angle equals exactly 90 degrees. In fact, it doesn't. I've drawn this so that that angle there is an angle of 89.6 degrees. So it's close to being a right angle, and it may look like a right angle to the naked eye, but none of the special right angle properties are true. And in upcoming videos, we'll be talking more about special right angle properties. None of the special right angle properties are true if the angle is close to 90, but not exactly 90. Very important. So you cannot assume that two lines are perpendicular unless you have some sort of justification for doing so. One term I will introduce, which probably will not appear on the test, is congruent. Congruent is like equal for shapes. We use the concept of equal for a number and the very similar concept of congruent for shapes. Two shapes are congruent if they have the same shape and the same size. They don't have to have the same orientation. So for example, the purple and the green shapes here are congruent. One is flipped over from the other. One you could say is a right-handed version and the other is a left-handed version, but it is the same shape fundamentally. These two are congruent even though they have different orientations. A bisector cuts something into two congruent pieces. An angle bisector cuts an angle into two smaller congruent angles. So for example, here we have an angle bisector. If we're told, for example, that the big angle, PNM, is 40 degrees, and that NQ bisects the angle, then we can deduce that the two smaller angles each have to be 20 degrees. They each have to be exactly half equal to each other because the angle was bisected. Similarly, the bisector of a segment may be a point, another line, another segment, or a line. The bisector divides the segment into two equal halves. So notice here, segment ST bisects PQ. Also notice it's definitely true that PQ does not bisect ST, because SR is clearly bigger than RT. So the fact that ST bisects PQ means that R is the midpoint of PQ, and that PR equals RQ. We've divided it into two equal halves. And again, that's always what bisecting means. Sometimes a line will bisect a segment and also be perpendicular to it. The line is called a perpendicular bisector of the segment. Line VW here is perpendicular. It's the perpendicular bisector of TU. Every point on the perpendicular bisector of a segment is equidistant from the two endpoints on the segment. And so that's a really handy fact to know. That shows up in a variety of ways. The perpendicular bisector, in fact, is the set of all possible points that are equidistant from the two endpoints of the segment. Now some basic facts about angles. We've already said that a straight line contains 180 degrees. This means that if two or more angles lie in a straight line, the sum of their angles is 180 degrees. So for example, we can assume that that long line is straight. It doesn't have some kind of slight bend at that point. The test will not do that to us. If it looks straight, it is straight. And therefore we know that those two angles together make 180. So x plus y equals 180. If the two angles add up to 180, then they are called supplementary. Two angles on a straight line are always supplementary. So P plus Q equals 180. When two lines cross, four angles are formed. So here we have two lines. They're going on forever in both directions. They happen to cross, and these four angles are formed. The pairs of angles opposite each other, sharing only the vertex in common, are called vertical angles. And vertical angles are always congruent. So for example, A and C, they don't share any sides. All A and C have in common is they touch at a single vertex. They touch at the vertex. B and D also touch at the vertex. And so that's why they're called vertical angles, because they meet at a vertex. So we know the vertical angles are congruent. We know that A equals C and B equals D. Of course, the pairs of angles next to each other, A plus B, B plus C, all of those are supplementary. They all add up to 180 degrees because we have pairs of angles on a line. Therefore, if we've given one angle in this diagram, we can find the other three. For example, if A equals 35, we know that C has to be equal. That also has to be 35 degrees. And B and D have to be the supplementary angle of 145 degrees. So that any two pairs together, any two angles together in a pair, add up to 180 degrees. Here's a practice problem. Pause the video, and then we'll talk about this. Okay. In the diagram, x equals 40 degrees, and RT bisects that big angle, SRU, which is a very big angle. Well, SRU is the supplementary angle to that 40 degree angle, so SRU has to be 180 minus 40, which would be 140. So SRU is 140. And this angle is bisected. Because it's bisected, it's cut into two equal halves. So those two halves, each one has to be 70 degrees. SRT equals 70 degrees, TRU equals 70 degrees. Those are the two equal halves of the angle that was bisected. Well, now notice that the angle TRV, that angle is made of TRU and angle X, which we know. We know TRU is 70 degrees. We know that angle X is 40 degrees. So we add them together. TRV has to be an angle of 110 degrees. Now notice that TRV is the vertical angle of SRW. So those two have to be equal. So that means that SRW also has to be a 110 degree angle. So Y equals 110. Finally, we will review parallel lines. If two lines are parallel, they never intersect, and they're always exactly the same distance apart. And again, this is another one of these properties like perpendicular. Close to parallel doesn't count for beans. You have to know that the two lines are exactly parallel. Obviously, since parallel lines never intersect, they never form angles with each other. We get many angles, though, if a third non-parallel line cuts across the two parallel lines. This third line is called a transversal. A transversal is a line that cuts across two parallel lines. So here we have a transversal cutting across the parallel lines WX and YZ. And we get 8 angles there. Now the 4 big angles are all equal, and the 4 little angles are all equal. So in other words, A equals D equals E equals H, and B equals C equals F equals G. That's the big idea. Now among these, of course, you may remember from geometry, there's all kinds of special names, alternate interior and same side exterior and corresponding angles. If you want to remember all those special names, that's great. You don't need to. All you need to remember is all the big angles are equal, all the little angles are equal. So here's the diagram again, and now I've labeled it so that it's clear that everything is equal. Also notice that P and Q are supplementary, so any big angle plus any little angle equals 180 degrees. That's a really big idea. Thus, if we were given the degree of any one of the angles here, we could find the other 7. In summary, we talked about lines and line segments, we talked about angles and degrees, we pointed out that there are 180 degrees in a straight angle and 90 degrees in a right angle. We talked about angle bisectors and perpendicular bisectors. An angle bisector divides an angle into 2 smaller equal angles. A perpendicular bisector is perpendicular to a segment and divides it into 2 equal halves. We talked about how 2 angles on a line are supplementary, vertical angles are congruent, and we talked about the angles formed by a transversal intersecting a pair of parallel lines. And we will talk about many applications of these fundamental ideas in the upcoming videos. Now we can start talking about triangles. A triangle is a shape formed by 3 line segment sides. And of course, triangles are important. First of all, there's just a lot of important facts about triangles themselves, and also we can understand many other shapes by thinking of them as triangles put together. So they play a very important role in geometry. Let's talk about some basic terms for triangles. The line segments are called sides, obviously. Each corner where the 2 line segments meet, where there's an angle, we call that a vertex. And the plural of that word is vertices. So a triangle has 3 vertices. In fact, every triangle has exactly 3 sides and exactly 3 vertices. This video lesson concerns some of the basic facts that are true for all triangles, every single triangle on Earth. In later videos, we'll start talking about some special triangles, but this video is really about all triangles. The most important and most remarkable is that for any triangle, no matter what the individual angles are, the sum of the 3 angles inside any triangle on Earth is exactly 180 degrees. That is an absolutely remarkable fact, proved first by Mr. Euclid, and it is 100% true for all triangles. So, why is this true? Why would that remarkable fact be true? Well, think about it this way. Consider the following diagram. Triangle ABC could be any triangle. Line DE is drawn so that it is parallel to AC. So remember what we talked about in the last video when we have parallel lines and a transversal cutting across those parallel lines. Well, if we consider AB a transversal, then those 2 red angles, BAC and ABE, those 2 red angles are equal. Those are congruent angles there. If we consider BC a transversal, then the 2 blue angles, ACB and CBD, those are also congruent. And of course, whatever that yellow angle is in the middle, we can see that if we look along the line, those 3 angles add up to 180 degrees because they lie along a line. Red, yellow, blue, those 3 angles. And so it must mean that the 3 angles in the triangle also add up. Because it's the same angles, they also add up to 180 degrees. So that's why this works for any triangle. Understanding this may help you remember that fact and understand it a little more deeply. Now some helpful terms for angles. First of all, an acute angle is an angle less than 90 degrees. A right angle, of course, is 90 degrees, and an obtuse angle is more than 90 degrees. We'll be using these terms throughout our discussion of geometry, and it's possible that they could appear on the test. Because the sum of the angles in a triangle is always 180 degrees, a triangle cannot possibly have 2 right angles or 2 obtuse angles. At least 2 of the angles in any triangle have to be acute. A triangle could have 1 obtuse angle and 2 acute angles. So we have a diagram here. And incidentally, all the diagrams in these lesson videos are drawn to scale. So that is a scaled diagram of a triangle with 20, 120, and 40 degrees. A triangle could have 1 right angle and 2 acute angles. Here's a 30, 60, 90 triangle. Or a triangle could have 3 acute angles, so 50, 60, and 70 degrees. In a triangle, the angles at any vertex is between two sides. It touches those two sides, or you could say it's adjacent to those two sides. For example, angle ABC, the angle right here, touches side AB and side BC. It's adjacent to those two sides. The third side, the side that the angle does not touch, is opposite the angle. For example, that same angle ABC and side AC are opposite one another. So that's an important relationship, and we'll be talking about that a lot. The relationship of the angle and its opposite side. Now we can talk about another rule true for all triangles. The largest angle is always opposite the longest side. 100% of the time, the largest angle is opposite the longest side, and the smallest angle is always opposite the shortest side. In the triangle above, of course drawn to scale, AB is clearly the longest side, so that means that angle C has to be the largest angle. And in fact, angle C looks like it's obtuse. An obtuse angle in a triangle is always going to be the largest angle. BC is clearly the shortest side, and so that means that angle A must be the smallest angle. So we absolutely know that this is always true. The final rule that is true for all triangles is called the Triangle Inequality theorem. The Triangle Inequality theorem states in any triangle, the sum of any two sides must be greater than the third side. Notice this is a strict inequality. It's not greater than or equal to, but strictly greater than. Why is this true? Well, think about a triangle. Here's a typical triangle. Clearly, the shortest distance between 2 points has to be the straight line path. That's a fundamental geometric fact. The shortest distance between 2 points is always a straight line. Well, that means the shortest possible distance between point A and point C must be the segment AC, because AC is a straight path between A and C. The detour path from A to B to C has to be longer than AC, because AC, by definition, is the shortest possible path. Therefore, it must be true that that detour path, AB plus BC, has to be longer than AC. And we can say the same analogous thing for the other pairs of sides, that AC plus BC has to be bigger than AB by itself, and AB plus AC has to be bigger than BC by itself. Another way to think about the triangle inequality, suppose the sum of two sides was less than the third side. Suppose we tried to construct, say, a triangle with lengths 2, 3, and 10. So here's a scale diagram, and you can kind of see there's a problem here, because no matter how we move that side of a 2 and a side of 3, we can rotate it all we want, they're not going to touch. No matter where we move those short arms, they are simply not going to reach across that gap to connect. So we're not actually going to be able to join it up and close off the shape as a triangle. So this does not form a legitimate triangle. It has to be closed. The 3 line segments all have to meet and enclose an area in order for it to be a triangle. So this will not work as a triangle. And this is why it's impossible to have two sides in a triangle that sum to less than the third side. What if the sum of the two sides equals the third side? Remember, the equals is not allowed by the triangle inequality either. It's a strict greater than. So what's the problem with equals? Well, what happens if we try and construct a triangle with sides 4, 6, and 10? So 4 plus 6 equals 10. What's going on here? Well, you see the problem here. I mean, yes, we can get the side of 6 and the side of 4 to connect up with each other, but the problem is everything is flat. And what we have, there's not really a geometric word for it, so I'm going to call it a flat thing. That flat thing is not a triangle. A triangle has to have an inside. It has to have area. So this flat thing does not meet our requirement for what a triangle is. This is what happens if we have two sides equal. Their sum is equal to to the third side. And so this is why not only the less than case is excluded, but also the equal to case is excluded. The sum of two sides has to be greater and only greater than the third side. Suppose we know that two sides of a triangle are 8 and 13, and we want to know the possible lengths of the third side. Well, certainly it's true that if we take the sum of the unknown side plus 8, it has to be bigger than 13. Well, from this inequality, we could subtract 8 from both sides, and it means that that x has to be greater than 5. So that's one of the statements we have. And notice that 5 is the difference of 8 and 13. It's also true that the sum of 8 and 13 must be greater than that third side. So it means that x has to be less than 21. Notice that's the sum of the two sides. So we can say that x must be greater than 5 and less than 21. That's the allowable range for x. And in particular, notice that it is greater than the difference of the sides and less than the sum of the sides. Well, we can generalize this. If we know that the lengths of two of the three sides of a triangle, we know that they're P and Q, then the third side has to be greater than the difference and less than the sum. Any side of a triangle must be more than the difference of the other two sides and less than the sum of the other two sides. So this is an alternate way to state the triangle inequality. In summary, the sum of three angles in any triangle must be 180 degrees. That's the really big one, true for all triangles. Two angles of a triangle must be acute. The third one could be acute, right, or obtuse, but it's true for any triangle that at least two of the angles are acute. Another property true for all triangles, the biggest angle is always opposite the largest side, and the smallest angle is always opposite the shortest side, true for all triangles. The sum of any two sides of a triangle is greater than the third side, true for all triangles. And another way to say that is, any side of a triangle must be greater than the difference of the other two sides and less than the sum of the other two sides. Everything on this summary is true for every triangle on Earth. Assumption and estimation. On the GRE, what are we allowed to assume from diagrams and what are we not allowed to assume? First of all, we are always allowed to assume that lines that look straight actually are straight. So suppose we're given this diagram. It certainly looks as if, as we go from B to A to C, what we have is a straight line. Well, technically, if someone wanted to fool us, instead of being exactly 180 degrees, the angle at A could be, say, 179.9 degrees, and it would look straight to us, but there'd be a slight bend at A. Well, we are guaranteed the GRE is not going to play that trick. If something looks like a straight line on the GRE, that is money in the bank. It absolutely is a straight line. So that's one thing you can trust. If it looks straight, it is straight. That's the good news. Well, as it turns out, you can't always trust how things look, and most things you can't trust about diagrams. If two lengths look the same but no other indication is given, then you can't assume that they are the same. If two lines look parallel and perpendicular and no other indication is given, then you can't assume these things. If angles look acute, they may be obtuse or vice versa. You can't even assume relative sizes. If one thing is drawn the same size or longer than another, you can't assume that that is true. And in fact, even if you're told that you have diagrams drawn to scale, so these are in fact two drawn to scale diagrams. Certainly looks like what we have is a right angle and a square here. It's very tempting to assume, yeah, a right angle and yeah, a square, but that's not the case. Even if things are drawn to scale, here I've drawn angle FEG 89.9 degrees. So that's not a right angle. That is not a right triangle. In fact, triangle FEG is really an acute triangle with three angles less than 90 degrees. Similarly, JKLM is not even pretending to be a square. None of the four angles are right angles. All of them are different from 90 degrees. Three of the sides are the same, but side LM is different. So that is not even vaguely like a square. So even if you were guaranteed that the diagrams were drawn to scale, there's a lot that you could not visually assume. So we can run into all kinds of trouble if we are naive in the way we interpret diagrams on the GRE. What can we trust about a GRE diagram? Well, it turns out on the GRE quant section, not much at all. Be very suspicious of any diagram drawn on the GRE. The following quote appears in the GRE official guide and at the beginning of the GRE quant section on the test. Geometric figures such as lines, circles, and triangles, quadrilaterals are not necessarily drawn to scale. In other words, give up all hope of trusting that the diagram actually looks the way it is drawn. So you should not assume that quantities such as lengths or angles are as they appear. You should assume that straight lines are straight. We've talked about that. That points on a line are in the order shown, and that more generally all objects are in their relative positions. So relative positions we can assume what's on the left, what's on the right, but we cannot assume size. We cannot assume what's bigger or what's smaller, anything like that from the diagram. They want us to base all our answers on geometric reasoning and deduction, not on estimation or comparing quantities by sight or measurement. So that is incredibly important. And it's extremely important to appreciate all the implications of that paragraph. For example, suppose the GRE gives us this diagram for a question. Certainly looks like a square, doesn't it? What the GRE is doing is they're baiting you. They're baiting you to make the assumption that, yes, what you have there is a perfect square. If they draw that diagram, there's no guarantee that the shape actually looks that way. J, K, L, M will be in that order, that we know, and there will be four sides, but it could be any of these. So any of these could be the right shape, the real shape, and the square drawn is really deceptive. But the GRE is making sure that you're not blindly trusting the shape drawn. You have to realize that the shape may not be drawn to scale at all. That is very important to appreciate. So if you're looking at that thing that looks like a square, it could be any of these four shapes at the bottom. We can't assume equal lengths. We can't assume horizontal or vertical. We can't assume parallel or perpendicular. We can't assume right angles. We can assume none of those from the diagram, but if we're told something is true from the text of the problem, we know that, and we know anything we can deduce from that. So you can trust your geometric deductions, and we'll be talking more about this in coming videos, what you can deduce from geometry itself. We can't trust lengths and angles as they appear, but we can trust information given in the diagram. So we're given this. That diagram actually contains two valid pieces of information. In that diagram, we absolutely know that side PR has a length of 8. And we absolutely know that QPR is a right angle. It's 90-degree angle because the little perpendicular sign is drawn. So those we know. We know nothing from this diagram. We know nothing about QP. QP might be less than 8. It might be equal to 8. It might be greater than 8. We know that QR is the hypotenuse, so we can deduce that QR is the longest side, and therefore it must be longer than 8. So those are things we can figure out from the diagram. And of course, we'd need more information in order to find anything here. Also in this diagram, well, we know we have a 40-degree angle and a 50-degree angle. Now we think about the theorem that says the three angles have to add up to 180 degrees. Well, 40 plus 50 is 90. 180 minus 90 is 90. So that means the angle at D has to be a 90-degree angle also. So that's something we can deduce. So we're not judging how does the picture look. We're making a logical deduction. Logical deduction you can trust. If you arrive there by a logical deduction, you absolutely can trust it. So that's how we know in this particular diagram that it's 90 degrees. And it is not assuming. Because we know it as a geometric deduction, deductions from the rules of geometry are exactly what you should trust on the GRE, not how the diagrams look. In summary, on the GRE, we can assume that a line that looks straight, in fact, is straight, but we cannot assume virtually anything else purely from the diagram. We must rely on the facts and relations specified in the problem text or in special symbols in the diagram. The GRE will lay traps giving misleading diagrams and encouraging naive students to fall into unwarranted assumptions. Do not naively trust the diagrams on the GRE. That's the big takeaway. Now we can talk about some geometry strategies. Geometry is primarily visual, and it demands visual as much as logical skills. So always do geometry with a diagram. It's very important to use the visual part of your brain in thinking through geometry. Sometimes the problem will give you one. If it doesn't, draw one of your own. And even if it does, it's good to redraw it on your scrap paper so you can mark it up yourself. So what do I mean by this? So when you draw it yourself, you can add any information given in the problem, because sometimes information will be given in the text, but it won't be in the problem that the test gives. And then you can also add any information that you can deduce yourself. Remember, the little square is a very good abbreviation for perpendicular. The test also uses that symbol. Arrows, such as this, are good symbols for parallel, to show two lines are parallel. Now, the test will not use this symbol, but it's still a very good abbreviation to use in your own diagrams. It may be helpful to extend lines in a diagram or to add a line that will facilitate a calculation, and we'll see this as we move through this module. In some problems, it will be helpful to assign variables either to the lengths or to the angles so that you can use algebra to solve. And finally, you need the visual ability to dissect a diagram. Now, what do I mean by this? And the best way to explain this is with this practice problem. So here's a practice problem. Pause the video and find x. Okay, let's talk about this. Now, you may look at this and you may think, oh dear, okay. So let's see, we have to find this angle, and that would allow us to find that angle. And then we can slowly work our way over. Maybe we can find one of the angles over here or over here someplace. Well, that's going to be a laborious way to go about this problem. And it's not really clear that that's even going to allow us to solve. Well, notice the following. Instead of looking at all these little triangles here, instead, we can look at this one big triangle. And of course, in any triangle, the sum of the three angles has to be 180 degrees. Doesn't matter the size of the triangle. Could be a big triangle or small triangle. Well, here's a big triangle. We know the 95. We know the 40. We want the x. So x equals 180 minus 95 minus 40. So x is 45. So it's very important when you have a diagram with a lot of detail that you're able to go back and forth, look little and look big. Because, of course, anything that's true of a little triangle could also be true of a big triangle. So, very important skill. In summary, always draw a diagram. Even if one is given, it's good practice to draw it yourself. You get your hands involved. That involves part of your brain. You involve your visual intelligence, very important. Then you can label it with what you are told and what you can deduce. You may have to extend a line or introduce a new line. We'll talk more about that in upcoming lessons. You may have to assign variables to lengths or angles and do some algebra. And finally, in diagrams, remember to look big and look small. So look at all the details as well as look at the larger shapes, and remember that the properties can apply to any, larger or smaller. In the first triangle video, we talked about ideas that were true for all triangles. Now we're going to limit things and just begin with two special categories of triangles, isosceles triangles and equilateral triangles. An isosceles triangle is one in which two sides are equal. For example, here we have an isosceles triangle, ABC. Such a triangle would also have equal angles, opposites of the sides. So this angle here equals this angle here. In fact, Euclid's remarkable theorem about these is a two-way theorem. In other words, if we know that the two sides are equal, then we can conclude that the two angles are equal. If we know that the two angles are equal, then we can conclude that the two sides are equal. So it's important to know that the logic goes both ways there. Could an isosceles triangle have a right angle? Could it have an obtuse angle? Absolutely. So for example, DEF is a right isosceles triangle, and JKL is an obtuse isosceles triangle. And in fact, we could find the other angles in each case. And so we could have one large angle and then two small equal angles. An equilateral triangle has 3 equal sides and 3 equal angles. All the angles have to be 60 degrees. So this is an equilateral triangle. Is an equilateral triangle also an isosceles triangle? Technically, yes. Technically, the definition of an isosceles triangle is a triangle with 2 or more equal sides. So equilateral is included. In all likelihood, the test will not ask you directly about that distinction. They will not ask you, is an equilateral triangle isosceles or not? That's not the type of thing they're going to ask. But you need to know that every special fact about isosceles triangles automatically applies to equilateral triangles as well. That you need to know. Now we will return for a moment to all triangles. The area of a triangle is how much space the triangle takes up. If the units used, this area, of course, is measured in square units, such as square inch or centimeters squared, that sort of thing. You may remember the formula, area equals 1/2 base times height, where b is the base and h is the height. But those problematic terms need to be clarified. What exactly is the base of a triangle? Naive students will say the bottom side, but that is not the whole answer. In fact, that's kind of a misleading way to think about it. Part of the problem is that some textbooks often insist on representing every triangle in the world with a horizontal line on the bottom. And this overrepresentation of one orientation misleads students into mistakenly thinking that every triangle automatically comes with a horizontal bottom side. And that's simply not the case. So here's a triangle, perfectly good triangle. There's no horizontal line in this triangle. What exactly is the base? Well, it turns out base has nothing to do with being horizontal. In fact, in any triangle, any of the 3 sides could be the base. There are actually 3 different bases, and we call it a base when we use that side to find the area. So AB could be the base, AC could be the base, or BC could be the base. Any 3 of those could be the base. That's important idea number 1. Now, what's exactly the height of the triangle? Just as students naively assume that the base is horizontal, they naively assume that the height is vertical. Neither one of those is necessarily true. In fact, h is a length of a segment called the altitude. So approximately, the altitude is a segment from a vertex to an opposite side that is perpendicular to that side. And so, in other words, whichever side we're using, that side is going to be the base, and then the altitude is perpendicular to the base, and it goes through the opposite vertex. Just as any side can be the base, we can draw an altitude from any vertex to any opposite side. So here's the same triangle. In the first triangle, we're using AC as the base, and we draw altitude BD. In the second triangle, we're using BC as the base, and we draw altitude AE. In the third triangle, we use AB as the base, and we draw altitude CF. So we have 3 different ways to pick the base, 3 different possible altitudes, and hence 3 different ways to find the area. Now here we're not given any numbers. Presumably in a problem you would only be given certain numbers, but you have at least the possibility of finding the area in these 3 different ways, depending on which numbers you were given. Now I'll point out this rough definition of an altitude is fine in triangles in which all 3 angles are acute. But think about an obtuse triangle. There's no way to draw a segment from point P to line M. Any segment that's going to go through line M is not going to be perpendicular. There's no way to draw a perpendicular line that goes through P and intersects MN. So what we actually have to do here is we have to extend the line. We have to extend NM, extend that segment out along a line, and then we can draw a segment from P that is perpendicular to that extended segment. So here, if NM Mn is the base, then PR is the altitude. And we can find the area base times altitude. And of course, we could also draw the altitude from N to MP, or we could extend segment NP and draw altitude MT. And this gives us two more ways to find the area of the same triangle. And of course, if we actually had numbers, of course, all three ways of calculating the area would lead to the same area, because a triangle only has one area, no matter which way we calculate it. Notice that in right triangles, two of the altitudes would be legs, the sides that meet at the right angle. If one leg is the base, the other leg is the height, and then either way, the area equals 1/2 times the product of the legs. So area equals 1/2 of AC times BC. Students sometimes worry about how to find the length of the altitude, how to find the height. The test will not simply give you the three sides and expect you to find an altitude or expect you to find the area. That is something you could do with trigonometry, but that is well beyond what the test is going to ask. One thing to keep in mind is the altitude always forms smaller right triangles within any triangle. This means that sometimes we might use the Pythagorean theorem or another right triangle fact to find an altitude. We'll discuss that more in the next video. Here's a practice problem. Pause the video and then we'll talk about this. Okay. In the diagram, two altitudes are drawn. Find the length of G. And so GF. So this is very interesting. We've extended line FH and then drawn altitude GX to it. And so GX is an altitude and FH is a base. We also have extended line GF and drawn altitude HY. And so HY is an altitude and GF is a base. So we have two different ways of figuring out the area. First of all, we could figure out the area using FH as the base and GX as the height. And we have numbers for both of those. So this is going to be 1/2 14 times 6. I'm just going to leave that in unmultiplied form for a moment. But notice I could also find it in a completely different way, using the other altitude and the other base. So now I'm going to use the base GF and the altitude HY. So this is another way to figure out. Here I know HY is 7, but I don't know FG or GF. In fact, that's exactly what I need to find. But now notice that we have two different expressions for area, but of course these have to be equal, because if the triangle only has one area, and so any way of calculating it should lead to the same number. So we can actually set those two equal. We can cancel the 1/2s, divide by 7, and then we get FG equals 2 times 6, which is 12. And that's the answer. Now we're going to talk about 4 kinds of lines in a triangle. You will not need to know these names, but you will need to keep these ideas straight. You will need to keep straight what you can and can't conclude. The first line that we've already talked about is the altitude. And this goes through the vertex and is perpendicular either to the opposite side or at least perpendicular to the segment extending the opposite side. That's an altitude. Always makes a right angle. Obviously, the point where the altitude intersects the opposite side usually isn't the midpoint. So here S does not happen to be the midpoint. It's just some random point on segment PR. The second special line is the perpendicular bisector. So this also makes a right angle, but this bisects a line at its midpoint. And notice that this one doesn't necessarily go through the opposite vertex at all. So the green line is the perpendicular bisector, and this is not even pretending to try to go through Q. It just misses Q entirely. But M is the midpoint, and so it is dividing
PR in half. And one thing that's special about a perpendicular bisector, every point on there is equidistant from point P and point R. The third special line from a vertex goes from the vertex to the midpoint of the opposite side. And this is called the median. You don't need to know that word. But the big idea here is that in a general triangle, the median divides the opposite side in half, but it does not necessarily divide the angle in half. And so we definitely know that PM equals MR because M is a median, but in general, it's going to be true that those two angles at Q are not equal to each other. So that's really important to know. If you're told that something intersects a midpoint, you cannot simply conclude that the two angles are equal also. Conversely, the fourth special line is called an angle bisector. The job of an angle bisector is to cut the angle in half. So it bisects the angle, divides the angle in half, but usually it doesn't divide the opposite side in half. And so here we can see quite clearly V is certainly not the midpoint of PR. So the two angles at Q are now equal, but clearly PV and VR are two completely different lengths. You have to appreciate what is and isn't true in most triangles in order to appreciate the special thing that happens only in an isosceles triangle. The line down the middle of an isosceles triangle from the vertex to the midpoint of the base plays all four of these roles at once. So in other words, point T is the midpoint of the base. That means that GT is perpendicular to the base at F, and it means that GT bisects the angle at G's. And so we know that we get equal angles up here. We know that these two segments are equal. We know that all of these qualities are true all at once because it's an isosceles triangle. And that coincidence of those four lines all playing the same role only happens in an isosceles triangle. The four special lines are four different lines in most ordinary triangles, and certainly in all non-isosceles triangles. And so we get information that one segment is playing more than one role. It's both perpendicular and an angle bisector, for example. That's enough to prove that the triangle is isosceles. The midline in an isosceles triangle is a line of symmetry, so it divides the bigger triangle into two congruent right triangles. Of course, all these triangle facts apply to the equilateral triangle, which is a special case of isosceles. In summary, an isosceles triangle has equal side lengths and opposite equal angles. Equilateral triangle has three equal sides and all 60-degree angles. Area equals 1/2 base times height. The base can be any side, and the altitude is perpendicular to that side. And then we talked about the altitude, the perpendicular bisector, the line from the vertex to the opposite midpoint called the median, and the angle bisector. And these are four completely different lines in most triangles, but the line of symmetry in an isosceles triangle plays all four of those roles at once. And so that is one of the magical qualities of an isosceles triangle.
Okay, now we can talk about right triangles. Right triangles are triangles that contain one right angle, that is, an angle of 90 degrees. Obviously, each of the other two angles must be acute, that is, less than 90 degrees. That's the only way that they would all add up to 180 degrees. First, we need to learn two important terms associated with right triangles. The two sides that meet at the right angle are called legs, and the side opposite the right angle is called the hypotenuse. So we mentioned legs briefly in the previous video, but here's the formal definition of legs, and also you need to know the word hypotenuse. So we have two legs here in a right triangle, and then the long side is the hypotenuse. In this triangle, AC and BC are the legs, and AB is the hypotenuse. The hypotenuse is always opposite the largest angle. The 90-degree angle is always going to be the largest angle. And so the hypotenuse is always the longest side of a right triangle. The three sides of a right triangle are related by one of the most important theorems in all of mathematics, the Pythagorean theorem. This theorem is attributed to Mr. Pythagoras, who lived back in BC times, and this theorem is the special property that separates all right triangles from all non-right triangles. So here's the amazing theorem. If the triangle is a right triangle, then a squared plus b squared equals c squared. Notice this works only for right triangles. If the triangle is not right, if the angle is close to being right, for example, if the angle is 89.99 instead of 90, then this theorem does not work. Notice that this is leg squared plus leg squared equals hypotenuse squared. It's lengthier to say that, but notice that what we're doing is we're squaring the two legs, adding them together, and that equals the hypotenuse squared. Now that's very important because, of course, we can change the letters around, but it won't change that relationship. Notice also this is a two-way theorem. What do I mean by that? If we know the triangle is a right triangle, then we can use the formula a squared plus b squared equals c squared. If we know the formula a squared plus b squared equals c squared works with the sides of a triangle, then we can deduce that the angle opposite the c is a right angle. So we can use this we can use the right angle to deduce that we can use the formula, or if the formula works, we can deduce that we have a right angle. It works either way. Here's a practice problem. Pause the video and then we'll talk about this. Okay, those of you who are familiar with Pythagorean triplets, you may see a shortcut here. Pretend we don't know about the Pythagorean triplets for a second. Let's just follow the ordinary logic of the Pythagorean theorem here. So, just for the practice, we know that a squared plus b squared equals c squared. We'll plug in a equals 6, b equals 8. We'll plug these in, square them. 36 plus 64 equals 100. So if c squared equals 100, the square root of that would be 10. And what we have is a 6, 8, 10 triangle. And of course, this is not any surprise if you remember your Pythagorean triplets. We'll talk about those in a moment if you're unfamiliar with that term. Here's another practice problem. Pause the video and then we'll talk about this. So some people might think, well, gee, this is the same problem over again. We got 6 and 8, so of course c equals 10. But look closely at the triangle. Right now, B is the hypotenuse, not C. And so B is the longest side. In fact, C is the shortest side. And so there's no way that C could be 10. There's no way it could be longer than the hypotenuse. So the problem here is that here the letters have been flipped around. Now, this is a little bit devious. It's debatable whether the test would actually do this to you, but theoretically this would be fair game. You can't just believe in the letters. You have to understand the relationships. And what the Pythagorean theorem says is that leg squared plus leg squared equals hypotenuse squared. So technically, in this triangle, b squared equals a squared plus c squared. And so if we want to solve for c squared, we have to subtract a squared. C squared equals b squared minus a squared. 8 squared minus 6 squared, 64 minus 36, which is 28. Take the square root of that. Of course, we remember from previous modules how to simplify a square root. We can simplify that to 2 root 7, and that is the length of c. That is the simplified form that would be listed on the test. Again, if you're not familiar with the idea of simplifying square roots, I suggest go back to the power and roots module where this is discussed in depth. Here's another one involving roots. Pause the video and then we'll talk about this. As might be apparent, the Pythagorean theorem really allows for no end of practice with square roots and operations with square roots. And again, if this is stuff that is unfamiliar to you, go back to the power and roots video and watch the video on operations with roots. That's exactly what we're doing here. So here we have the bona fide Pythagorean theorem, a squared plus b squared equals c squared. We're going to square those two radicals. Of course, square root of 7 squared is just 7. 2 root 5 squared, well, that's 2 squared times root 5 squared, so that's 4 times 5, which is 20, and so that adds up to 27. And so c squared, c should equal the square root of 27. We can simplify that because, of course, that's 9 times 3. Square root of 9 is 3, so this simplifies to 3 root 3. So this would be a triangle where all 3 sides are radical expressions. That happens sometimes. It can be very helpful to know the sets of integers that satisfy the Pythagorean theorem equation. These sets of 3 integers are called Pythagorean triplets, and knowing them can be a huge time saver on the test. The simplest Pythagorean triplet is 3, 4, 5. So here's a 3, 4, 5 triangle. Notice that we don't even need to draw the perpendicular symbol. Just by the fact that the sides satisfy the equation a squared plus b squared equals c squared, that's enough to guarantee we absolutely know that we have a right angle there because those numbers obey the formula. 2 other Pythagorean triplets that the test likes are 5, 12, 13 and 8, 15, 17. Those are good ones to memorize. Sometimes in advanced questions they will also use 7, 24, 25. That one is rare, but if you really want to be safe, you should memorize that one also. Notice we could also multiply any of these fundamental triplets by any number to create a new set of 3 numbers. So starting with 3, 4, 5, we could multiply that by 2 and get 6, 8, 10. Multiply it by 3 and get 9, 12, 15. By 4, by 5, by 6, by 7, by 8, and so forth. Similarly, we could find multiples of 5, 12, 13, or 8, 15, 17. So you really don't have to memorize all the multiples. All you have to do is memorize those starting ones, those 4 starting triplets, and then you can easily find the multiples if you need them. Now this leads us to a discussion of proportional reasoning in right triangles. The test could give you a right triangle with 2 sides that are relatively large numbers. So technically, if we wanted to find x, we'd have to do 24 squared plus 45 squared equals x squared. In this problem, it would be a huge mistake to square 45, that would be some really big number, square 24, that would be another big number, add those 2 numbers together, and try to find the square root of the resultant 4-digit number. That would be a spectacularly bad idea. Instead, find the greatest common factor of the sides and factor that out. Well, the greatest common factor of 24 and 45 is 3. Okay, well think about it this way. Suppose we scale down that triangle by a factor of 3, a scale factor of 3. So we have the large triangle, our starting triangle, and then we have a scaled down version with the unknown hypotenuse y. Well, of course, that scaled down version, that looks pretty good because that's actually one of our Pythagorean triplets. Of course, that's the 8, 15, 17 triplet. We don't even have to do any calculations. We can see instantly, well, of course, y just has to equal 17. Well, once we know that, then it's going to be very easy to find x. We just have to scale back up. So we got to the smaller one by dividing by 3. We get to the larger one by multiplying by 3. So x should just equal 3 times 17, which is 51. And so basically with almost no calculations, really no calculation we did here is 3 times 17, that was enough to solve this problem. We never had to deal with 4-digit numbers. That's really important. Basically, almost any time on the test that you're finding yourself dealing with 4-digit numbers that are not numbers given in the problem, chances are you're making your life much harder than it has to be. It may be that when we factor out the greatest common factor, we will get one of our time-saving Pythagorean triplets. Otherwise, it may be that we just wind up with a small triangle with some very easy numbers and we can just quickly apply the Pythagorean triplet in the Pythagorean theorem in that much smaller triangle. So here's the problem. Pause the video and we'll talk about this. Well, the greatest common factor of 36 and 72 is 36. If we divide all the sides by 36, we get a triangle with legs of 1 and 2. Well, those are very simple numbers. If we have a equals 1 and b equals 2, Plug this into the Pythagorean theorem, we get c squared equals 5, c equals square root of 5. And so that means in the big triangle, all we'd have to do is multiply square root of 5 times 36. Multiply it back by that greatest common factor, and so rs equals 36 root 5. So notice we did our Pythagorean theorem with the small numbers. Very convenient. We never had to square 36 and square 72. That would just be a disaster. So you don't want to square gigantic numbers. You want to divide them down by a greatest common factor and then work with much smaller numbers. Here's another practice problem. Pause the video and then we'll talk about this. Okay, so obviously from what we've been talking about, we do not want to get into squaring 42 and squaring 56 and getting those huge numbers. We don't want to do that. Instead, we find the greatest common factor, which is 14. And 56 is 4 times 14, 42 is 3 times 14, so we'll just scale down to, we have a leg of 3 and a hypotenuse of 4. Notice this is not a 3, 4, 5 triangle because the hypotenuse is 4. Instead, what we have is b squared equals 4 squared minus 3 squared, 16 minus 9, which is 7. So b squared would be the square root of 7. And then we just scale back up by the factor of 14. The greatest common factor is the scale factor. We scale back up, and we get that x equals 14 root 7. In summary, right triangles have one 90-degree angle and two acute angles. Right triangles always have one hypotenuse, the longest side, and the two legs. The legs are the sides that touch the right angle. The Pythagorean theorem tells us that a squared plus b squared equals c squared. That's only true for right triangles, and in fact we know if it's a right triangle we can use that formula, and if the formula is true we can deduce that we have a right angle. It works both ways. We'll be making extensive use of this theorem in the remaining geometry videos. The Pythagorean triplets, these are very handy to have memorized because they save you a lot of time. If you know these, you can avoid all kinds of unnecessary calculations. And finally, if the sides given are larger, the sides of the triangle given are relatively large numbers, divide down by the greatest common factor, do the computations in the smaller triangle, and then scale back up. That is a much easier way to think about these problems. Now we can talk about similar triangles. Recall the idea of congruent. If shapes are congruent, it means they have the same shape and the same size. So for example, these are two congruent shapes. They don't have to be in the same orientation. We can flip them around, we can rotate them, but these are essentially the same shape, and so we could pair them up. The corresponding sides have equal length, the corresponding angles are equal. They are exactly the same shape, just in different orientations. Sometimes in geometry and in real life, we need to examine two figures that have the same shape, but different sizes. Two geometric figures with the same shape and different sizes are called similar. And so what we have here, those two shapes, it is the same shape. The second one is a smaller copy of the first one. And again, it's in a different orientation. It's been flipped around and rotated a little bit. But that is, in fact, the same shape. So the first thing we'll talk about are angles in similar figures. The first big idea of similar figures is that similar figures have equal angles. So B corresponds to J, so angle B has to equal angle J. Angle C has to equal angle K, and angle D has to equal angle L. And so each angle is equal to its corresponding angle in the similar triangle. Notice that if a segment goes across a triangle and is parallel to one of the sides, it automatically creates a smaller similar triangle. So GJ, if GJ is parallel to FK, well, that means that triangle HFK, the larger triangle, is similar to triangle HGJ, the smaller triangle. And it also means that the angles would be equal in both. Obviously, they both share the same angle at H. But angle, for example, angle HGJ would have to be equal to angle HFK. It's not hard to prove that two triangles are similar using their angles. If just two angles in one triangle are equal to two angles in another triangle, that's enough to establish that the two triangles are similar. So for example, here we know that the smaller triangle has a right angle, the larger triangle also has a right angle, so that's one thing they have in common, and they share that angle at P. And so that's another angle that, since it's common to both of them, they share that. That's two angles. That's enough right there to guarantee that those two triangles, the smaller triangle and the larger triangle, are similar. Now we can talk about sides in similar figures. The sides in similar figures are proportional. Well, what does that mean? This means that we can set up proportions. The ratio of any two sides of one triangle has to be equal to the ratio of the corresponding sides in the other triangle. So for example, if these are our similar triangles, the ratio of AB over BC, that has to equal the ratio of DE over EF. So setting those two ratios equal, that's the proportion we can set up. Here are the similar triangles again. Another way to write those is in the form of side of one triangle over the corresponding side of the other triangle. So we could write AB over DE. And the advantage of this is now we can create an equation that relates all the sides of both triangles. So AB over DE, those are corresponding sides. BC over EF, those are corresponding sides, and AC over DF, those are corresponding sides, so all three of those ratios have to be equal. If the sides of the bigger triangle are written in the numerator, and these fractions are greater than 1, and this quantity is known as a scale factor. So we use K for scale factor, so K would be D over E equals EF over BC equals DF over AC. If we know any length in the smaller triangle, the corresponding length in the larger triangle, it's just the original length times the scale factor. And in fact, the amazing thing is not just for the sides of the triangle, but any length at all. So for example, suppose we construct an altitude in the smaller triangle, or suppose we connect one of the vertices to the midpoint of the opposite side. Any length at all that we construct in the smaller triangle, if we construct that exact same length in the larger triangle, we'd multiply the length in the smaller triangle by the scale factor, and it would be the length in the larger triangle. So this is an incredibly powerful tool, scale factor. Here's a practice problem. Pause the video, and then we'll talk about this. Okay, so we have a segment that's parallel to the side, so we know that we have two similar triangles. FJ equals 4, that little segment, and GH and also JH equals 20. So GH is that opposite side, JH is part of the side, and we want to find the length EJ. Well, first of all, let's compare the two sides that are obviously corresponding sides. So we take the ratio of GH over FJ. This is going to be the scale factor. And of course, this is 20 over 4, so this is 5. So we don't know EJ, so let's just call that X. That's the thing we're looking for. We don't know it. We do know that EH would have to be 5X. It would have to be 5 times that length. Well, the number that we're actually given is JH. Well, notice that JH, that's 20. Of course, that has to equal EH minus EJ. So that's 5X minus X, which is 4X. Well, now we can solve for X. X equals 5, and that's the length of EJ. So that's a very easy problem to solve using the idea of scale factor. Now we'll talk about similar figures and area. This is a relatively rare topic that may show up on more challenging quant questions. So this is not always going to show up, but this could show up. If we know that every length in one shape gets multiplied by a scale factor to create another shape, then what is the relationship between the areas of the two shapes? Let's think about this for triangles. We know that the area of a triangle is given by area equals 1/2 base times height. Suppose each length increases by a scale factor k. Then b is multiplied by k, and h is also multiplied by k. That's 2 factors of k. This means that the area is multiplied by 2 factors of k. In other words, k squared. When lengths are multiplied by k, area is multiplied by k squared. Here's a practice problem. Pause the video and then we'll talk about this. So clearly the scale factor is the ratio of 30 divided by 6, which is 5. If the scale factor is 5, the scale factor squared is 25. The area is multiplied by 25. So the small one has an area of 12. The large one must have an area of 25 times 12. For that, we'll use the doubling and halving trick. Double 25 to 50, halve 12 to 6. Do it again. Actually, we don't even need to do it again. 6 times 50 is 300. That's pretty easy to see. So that's the area of the larger triangle. Here's a harder practice problem. Pause the video and then we'll talk about this. So clearly, we have two similar triangles, CDB and CAE, and BD corresponds to side AE. So we set up the ratio AE over BD. This will give us the scale factor. This is 40 divided by 5, which is 8. That's the scale factor. So the ratio of the areas is going to be the scale factor squared. Well, we can easily find the area of that small triangle. It's just a right triangle with legs of 5 and 10. So that area is going to be 1/2, 5 times 10, that's going to be 25. Well, the area of the larger triangle is going to be 64 times 25, scale factor squared times the smaller area. For this, we'll use doubling and halving. Half of 64 is 32. Half of 32 is 16. So we get 16 times 100 is 1600. That's the area of the large triangle. And of course, the shaded area is just large triangle minus small triangle. And so that's going to be 1600 minus 25, which is 1575. That's the area of the shaded region. In summary, similar figures have the same shape but different sizes. They're like expanded or shrunken down versions of the same shape. The angles in similar figures are always equal. We can prove two triangles are similar if they simply share two angles. Sides in similar figures are proportional. There's a number of ways we can set up those proportions. The scale factor k is the factor by which all lengths in the smaller figure were multiplied to arrive at the lengths in the larger figure. And finally, and this is the fact that may show up, that is not necessarily going to show up, only on more advanced problems. If all the lengths are multiplied by k, then the area is multiplied by the k squared, the scale factor squared.
Special right triangles. Now we're going to discuss two special right triangles, and the test writers are absolutely in love with these. Why? Because both have the property that with very little information, you can get all kinds of information. You can figure out all the sides and angles and figure out other things just from a little bit of information. So they love the fact that they can just give a little information and then you're expected to find all the rest. So these are very good triangles to know about. Triangle number one. The first is an isosceles right triangle. Think about that. It's a right triangle, has a right angle, but isosceles means two sides, the two legs, are equal. So the angles also must be equal, so it must be a 45, 45, 90 triangle. The two legs have equal length, and the hypotenuse is larger than either leg, though less than the sum of the legs. So let's consider a 45, 45, 90 triangle with legs that happen to have length of 1. We can find the hypotenuse with the Pythagorean theorem. So that's just 1 squared, or 1, plus 1 equals 2. And so the hypotenuse is the square root of 2. That was just one 45, 45, 90 triangle, but the big idea is that all others in the world are similar to that. So they all have the same ratios. So they all have 2 equal legs, and for all of them, the hypotenuse is root 2 times the length of the leg. We could think of the sides as the leg equals s, and the hypotenuse equals s times root 2. We can refer to this triangle in 3 different ways: the isosceles right triangle, the 45, 45, 90 triangle, or the 1, 1, root 2 triangle. You have to know this triangle very well, but do not simply memorize it. Instead, make sure you understand why each set of properties implies all the others. The more you can just start with one property and derive the others, the more you will really understand this triangle. Notice that we divide a square in half along the diagonal, we get 2 of these. This makes it very easy to see that the diagonal of a square equals the side times the square root of 2. That's also a handy fact to know. We can also divide a square into 4 of these triangles, and the hypotenuse of each is on the side of the square. So we're going to pause here for a minute to take a detour from geometry to discuss numbers. We're going to talk about rationalizing denominators. Now, those of you who watched the Powers and Roots module, this should be familiar to you, and this may be some helpful review. Some of you are coming directly to this lesson from a particular question, and you may be completely unfamiliar with this idea. I'm going to give a very brief overview here, but really, if this is a new idea to you, you probably should watch some of the lessons in Powers and Roots to get familiar with all the background of this. So, special right triangles often involve square roots and may involve fractions, so we have to consider the case of what to do if we have a square root in the denominator. A square root in the denominator is considered problematic for a variety of reasons. For example, the test will never list fraction answer choices with a square root in the denominator. So even if the correct answer is 7 over root 5, the test is never going to list an answer choice in that form. We fix this problem simply by multiplying the fraction by the radical over itself. So in particular, 7 over root 5. We want to get rid of that square root in the denominator, so we're going to multiply by root 5 over root 5. Of course, we can multiply by anything over itself, because anything over itself equals 1. Now notice what happens in the denominator. We get root 5 times root 5. Well, by definition, the square root of 5 times itself equals 5. And in the numerator, I just get 7 times root 5. So 7 root 5 over 5, that is considered the proper way to write this, without a radical in the denominator. And again, this was just a brief example, a very brief overview of the topic, rationalizing denominators, kind of a whirlwind tour of the idea. If this is new to you, brand new to you, probably a very good idea to watch the lesson on rationalizing, a full lesson on this one particular idea. In this lesson, we're just going to move forward and assume that you know this idea now. Here's a practice problem. Pause the video and then we'll talk about this. Okay, so we have a square, we have a 45-degree angle in that triangle, so that is an isosceles right triangle there, and we want the perimeter of the square. Very interesting. Well, first of all, we know that Kn, that's the leg of the triangle, it's also the side of the square, that times root 2 equals the hypotenuse, jk. So we certainly can say that Kn equals jk over root 2, or 6 over root 2. And immediately what we're going to do, because we have a radical in the denominator, we're going to rationalize. we're going to multiply that by root 2 over root 2. Then I'll get 6 root 2 over 2. 6 over 2 cancels to 3. So 3 root 2. So that is the rationalized expression for the length of Kn. Now the perimeter is just 4 times that. 4 times 3 root 2, or in other words 12 root 2. And we go to the answer choices and we select answer choice D. The second triangle. For this we will begin with an equilateral triangle in which each side has a length of 2. This triangle, while very symmetrical, is not a right triangle, of course. But we can create a right triangle by drawing an altitude from point A, essentially cutting the triangle in half with a line down the middle. As in any isosceles triangle, this altitude will bisect the angle at A and bisect the opposite side. So here it is with that line drawn, and now we can actually see the triangle that interests us in purple on the side there. The angle at B is one of the original 60-degree angles of the equilateral triangle, and the hypotenuse AB is one of the original sides. The angle at 30 degrees is the bisected angle, and DB is a bisected side. So we have the length of two sides. We have a leg of 1 and a hypotenuse of 2. Let's just say AD equals H. We can find H with the Pythagorean theorem. 2 squared plus 1 equals 1 squared plus H squared. In other words, H squared equals 4 minus 1 or 3, and H equals the square root of 3. So that is the length of AD. So sometimes this is called the 30, 60, 90 triangle. Sometimes it's called the 1, 2, root 3 triangle. It's very helpful to remember the relationship that this triangle has with the whole equilateral triangle from which it comes. In fact, one of the best ways to understand what's going on is kind of to draw the dotted other half of the full equilateral triangle so you can visualize it. As with the 45, 45, 90 triangle, any 30, 60, 90 triangle is similar to this one, and the sides are proportional. So we could say that the hypotenuse is always twice the length of the short leg. The long leg is always root 3 times the short leg. Now that we know the 30, 60, 90 triangle, we can create a general formula for the area of an equilateral triangle with side S. Create an altitude which divides the whole triangle into two 30, 60, 90 triangles. So the hypotenuse is S, so ML equals S over 2. And Km, the altitude, would have to equal S root 3 over 2. So Km is the altitude, and JL, which is equal to S, is the base. So of course area is 1/2 base times height, 1/2 S times S root 3 over 2, and this simplifies to S squared root 3 over 4. That is the formula for the area of an equilateral triangle that has a side of S. Now this is a very handy formula to know, but do not memorize it. Instead, make sure you can understand the argument and reproduce the result on your own. In other words, start with the equilateral, build the 30, 60, 90 triangle, and wind up with this formula. And if you can produce this same formula again and again, then you really understand it. Here's a practice problem. Pause the video and then we'll talk about this. All right, we want to find the perimeter of this triangle. It is a 30, 60, 90 triangle. Well, the short leg is half the hypotenuse, so the short leg is 4 root 3. The long leg is root 3 times the short leg. Well, 4 times root 3 times root 3. Well, root 3 times root 3 is just 3, so that's 4 times 3, which is 12. And so the hypotenuse is 4 root 3 plus 8 root 3, which is 12 root 3, plus 12. Here's a harder practice problem. Pause the video and then we'll talk about this. Okay, in the diagram, HJLM is a square. And we have GH, that slanty side, is 10. And of course, JK, because it's symmetrical, JK would also have to be 10. We have two 60-degree angles, so we have two 30, 60, 90 triangles, one on each side. So first of all, we can find the proportions. We know that GM equals 5. We know that HM equals 5 root 3. So one triangle would be 1/2 base times height, but we have two triangles here. So the area of the two triangles together is just going to be base of the triangle times the height, which is 5 times 5 root 3, or 25 root 3. That's the area of the two triangles. The square has a side of 5 root 3, so we square that, and we get 75. So the entire area is the square plus the two triangles, 75 plus 25 root 3. One special triangle, the isosceles right triangle, has angles of 45, 45, 90 and sides of 1, 1 root 2. The other results from dividing an equilateral in half and has angles of 30, 60, 90 and sides of 1, radical 3, and 2. We can use these patterns in proportional reasoning to solve a variety of problems.